Hey guys, welcome back. I wanted to cover two things that didn't make it into our previous video and what will hopefully be a relatively short video. I wanted to cover some common sampling schemes or sampling designs and common sources of bias. So of course, we want to minimize the bias in our data. I think it is very difficult to completely eliminate bias in our data. And then sampling schemes, similar to our discussion on study design, there's going to be a lot of logistics involved. People go with one over the other because logistically, some make sense where others don't. So let's go through it. Recall, this was one of our first lectures together, that we sampled from what is hopefully our intended population to draw valid inference. Remember the difference between descriptive statistics. We've been learning so far only descriptive statistics because they apply to the sample. The histogram describes our sample. It graphs our sample, not the population from which our sample came from. But in science, we are interested in making inference about the population, not the sample. So that's why folks have created these sampling schemes. Again, these are the common sampling schemes. I'm sure there are plenty of others. My goal is to introduce you to the most common few. All right, let's run through it. The simple random sample, and most commonly it is called the SRS. Yes, I'm quite aware that the next one also has SRS as the first letters, but whenever you see SRS, they're talking about the simple random sample. So here is the nebulous population that we are trying to sample. Remember that in 99.9% of the cases, we cannot possibly reach every single subject in the population. And so we simply, this is the simple random sample. Every subject in the population has equal chance of being included. Every subject in the population has an equal chance of being included in our sample. Well, that is a beautiful thing. But as you might imagine, that is very difficult to ensure in many realistic cases. But to illustrate the simple random sample, right? My data is going to be this black marker right here. I'm just going to randomly sample all right. There is my sample. Looks like the sample size, 1, 2, 3, 6, 8, 10. It has some average, has some standard deviation S, etc. We're very simple. If I stood here and I just did this, I would randomly sample from my population of interest. Simple random sample. Every subject in the population has an equal chance of being included in our sample. Okay. But as you might imagine, the more complex your population, the harder it is to ensure that every subject in your population has an equal chance of being included in your sample. And so we move on to more complicated schemes. And the first one is the stratified random sample. And the definition is that we first divide the population into meaningful strata. You can think of strata as arbitrary divisions. That makes sense for your research study. And then obtain a simple random sample within, and this is important, every stratum. So with a stratified random sample, we first think about, okay, I have this complicated population. I want to make sure that everybody, that my sample is as representative of this population as possible. And so I'm going to first divide my population into meaningful strata, meaningful to your specific study. So here I'm going to divide it into my strata. Okay, here are my strata. And now I'm going to produce a simple random sample inside of each strata. You could make it balanced. Balanced is when you have an equal number of samples per strata. It is not a requirement, but some people do strive for balance. Sometimes it's not feasible to have balance, but sometimes it's a nice thing to have if you have an equal number of data points per strata. My current example is not balanced. I just have 2 observations in these strata right here, and I have 3 observations here. I have 6 observations in this big stratum right there. So, the example to think of here is, okay, suppose I wanted to, and I'll just talk to the camera. Suppose I wanted to study some kind of a child health outcome. And I wanted to make sure that, my sample was representative of, as closely representative of the demographics in the state of Virginia. So Virginia, of course, has a huge southwest to northeast sort of gradient, for example, for income, as well as other socioeconomic, racial demographics. So one thing to do would be to define strata as schools, for example. So in my example, child health, maybe schools, call it elementary schools, as my strata. Now, there's probably 1,000 to 5,000 elementary schools in the state of Virginia. And then I would go in and obtain a simple random sample of, say, 10 children per school. Now, schools tend to draw from the local area, especially something like elementary school. Except for very rare circumstances, people tend to go to their local elementary school. And so the elementary schools are going to be representative of the varying demographics in the state of Virginia. And so by obtaining a simple random sample of something like 10 children in something like 1,000, several thousand elementary schools, I can obtain a pretty darn good sample of this very diverse population. Now, this costs a lot of money. Would cost a lot of money. Would cost a lot. money or time or resources, I would need to visit. If I was collecting the BMI, if I wanted to study childhood obesity, I would need to collect BMI from every single school. Now, I could have teachers perform this, but that's still, that is time away from teaching. Or I would send a nurse to every single school. Boy, that's a lot of time or a lot of nurses. So you can imagine this being a very, very good, very, very representative sample that is very, very time intensive and or costly to obtain, because you have to visit every strata. Every strata. So you can think of this being particularly attractive when there are relatively few reasonable strata. Maybe instead of doing every single school, I would divide the state of Virginia into, say, 5 regions, 5 or 10 regions, and I would obtain a sample of, say, 100 children from each region. Then I would need only, to send a nurse or, a doctor to one of 5 regions, not to, 3,000 schools. And I would be giving up some amount of, how representative my sample is for the sake of feasibility. Okay. In comes the next type of sampling, and that is cluster random sampling. And we're going to keep our child health example going, because I said, what would be great is if the schools would serve a strata and would obtain a small sample of children from every single school. But boy, is that expensive. So what a cluster random sample does is designed to sort of mitigate just that. I'll still divide my population into meaningful strata, arbitrary divisions. And now I obtain a simple random sample of the strata themselves. And this gives us the final sample. Because I now obtain a simple random sample of the strata and every subject therein, this can work. So with my child health example, I would divide my population into schools, right? So these green divisions are my schools. And now, instead of going to every single school and getting a simple random sample of children within that school, I would take a simple random sample of the strata themselves. So of the schools, I would say I'm going to take this one, this one, this one, and this one. And now every subject, these 3, these 2, these 3, and these 2, but not these, not these, and not these, and not these, would make it into my sample, right? So first, take a sample of all schools, all children in those schools are in the sample. You can sort of think of different logistical issues with which kind of which type of cluster or stratified random sample to go for. If you have a ton of meaningful strata and it is infeasible to visit every single one, then a cluster random sample will work. If you don't have a reasonable way of getting any strata at all, maybe a simple random sample works. If you have a relatively small number of strata and you are able to take a small simple random sample within each strata, then you go for the stratified random sample. So this last one, I only list it as its own category because I've actually only recently seen a few studies claim they're using a convenience sample. So a convenience sample, well, it's kind of exactly what it sounds like. It's a convenience sample it is just the most convenient sample available to researchers. Not necessarily representative. Okay, clearly this is suboptimal. That is a big, weird word for saying that is not a good thing. Convenience samples are not great, but you can imagine that during a pandemic, especially of an infectious disease that is deadly, it makes sense to use the most convenient sample to learn something, to learn, to study the spread of COVID somehow in your convenient sample. When you can't go to every school, when you can't go to even a sample of schools, you might be stuck with a convenient sample. It's suboptimal, and maybe, first of all, if you are working with a convenient sample, make sure to put that down in your methods section. It's up to the editor to either accept your paper or reject it, right? But I've seen these pop up more and more, and I think that is because just the nature of this fast-moving pandemic, sometimes we have to work with suboptimal samples. So if you see someone claim that they're using a convenient sample, they are admitting it is not a random sample. A good example of this is students in a class, students in intro to psychology class, students in intro to biostatistics class. It could be the patients currently in the ICU. Of UVA Medical Center. These are all samples that would be convenient, for example, for me to obtain. I can administer a survey to my intro to stats, biostat students. I can go and if I pass institutional review board for both of these, I can go and record something on the patients that are currently in the ICU in the med center, but these are not necessarily representative, right? UVA, for example, accepts something like 20% of applicants, not all of them in the state. So we have to be very careful about generalizing findings, right? We have to be very careful about generalizing findings from a convenience sample to the population. And that brings me to bias. Clearly, using a convenience sample will introduce bias. And specifically, very much so, this first kind of bias, selection bias, or sometimes it's called sampling bias. So selection bias occurs when the sample is not representative of the subgroups in the population. Suppose in the population, there are 50%, close to 50% men and 50% women, but in your sample, there are 75% men. That is an example of selection bias. Your sample is not representative of all the subgroups in the population. And this occurs quite commonly, frequently occurs, with convenience samples. As we talked about, sometimes that's just the price we have to pay for getting any data at all, right? Any data is better than no data, but we have to be careful about extrapolating to what population can we extrapolate our findings, to what population can we extrapolate our inferences. The next one, response bias, is another very practical sort of logistical issue. And it's sort of a blanket term. Response bias. Subjects provide false or inaccurate data. Subjects provide false or inaccurate data. You have devised a beautifully representative sample. You go to obtain your survey, or you go to take measurements. And especially if you're administering a survey, your subjects can just lie. They can just mislead you. This can occur for sensitive topics, and can be, or tends to be, more common with self-reported data. What I hear from students all the time is, well, how do we know? How can we possibly know? You can have an inkling, and sometimes you will not know. This is why I started by saying it is probably impossible to eliminate all bias from the study, but it is possible to treat, questions or data collection around some sensitive topics to minimize your expected response bias. Depending on the question, you can either administer it individually to subjects through an individual interview, or it's possible that for some sensitive topics, you will get more truthful answers in a group. So this has to do with the design of the instrument, more so than saying there could be something that completely eliminates all response bias. Subjects lie to us, subjects can forget, and we will still get inaccurate data. Subjects can, of course, mislead. It's about designing, maybe eliminating or minimizing opportunities to provide self-reported data. Actually taking measurements, if we're interested in BMI, taking measurements of height and weight, for example, so that we can compute our own BMI, not asking people to provide self-reported height and weight. And if we're interested in sensitive topics, then we have to follow sort of guidelines that are outside the scope of this class, that are sort of subject specific, and field specific to minimize response bias as much as possible. The last one, non-response bias. Also very much tends to do with how we are asking the questions, how we're trying to reach our subjects. Non-response bias. Some subjects identified in the sample cannot be reached for a response. Some subjects that made it into our beautiful representative sample that costs us so much time and money to put together just cannot be reached. You know, is it with my child health example, we've identified, you know, we're taking simple random samples inside every single elementary school in Virginia, but when we come to measure BMI of the children, there are some children who are not there, they're absent. They simply cannot be reached. Is there something systematic about absenteeism that will inform my my bias, the presence of bias? This tends to be, often occurs in surveys where only a single method, for example, phone or internet, is used to reach subjects. If we're only using phone to administer a survey, then we are, you know, there are some people who do not have a home phone. If we're only calling landlines, for example, we are definitely not reaching everybody with a cell phone. If we're calling both landlines and cell phones, there are people who do not have a cell phone. Now, this is a diminishing number of people who have neither a landline nor a cell phone, but still, there are many, many surveys that are internet-only surveys, and those should raise red flags in terms of selection bias, who is visiting that website, response bias, you know, are the questions worded in a way that promotes accurate data collection, and non-response bias. If we're only collecting things via the internet, not everybody's on the internet. You know, we might be excluding rural customers that way. And so that is definitely one to watch out for. Non-response bias often has to do with how data are collected. And again, it's impossible to eliminate all bias, but it is, we often want to design the method of collecting data, the kind of data we collect, how we ask the questions to minimize the biases therein. All right, guys, thank you so much for your attention, and I will see you in class.